Hello, everyone, and thank you for joining us for the monthly meeting of the Canadian Aviation Historical Society Manitoba chapter. My name is Jim Bell. I'm chapter president. Our speaker this evening is Gilles Messier. He will be speaking about the history of sounding rockets and the Black Brant, Manitoba-made Black Brant in particular. Gilles is a bit of a polymath. He is a writer, an author, an artist, playwright, and he has presented to us a couple of other times on space subjects. So I'm sure you'll find this quite interesting. And without anything else, Gilles Messier.
All right, thank you, Jim. Yeah, so most of you have probably already met me at previous meetings. If not, like I said, my name is Gilles. Up until very recently, I worked as an engineer, but I got out of that and I now make my living writing history and science videos for the YouTube channel Today I Found Out, so a bit of a change of career there. One of my favorite historical subjects, as I said, is space exploration and rocket technology, which is why I'm going to be presenting today on sounding rockets. Now, I find these particularly fascinating because, well, I used to do sailing when I was much younger, and they have a saying, which is that the big boats get the glory and the small boats make the sailor. And I think it's very much the same if you look at the history of rocket technology. The larger rockets, the Saturn V, Soyuz, Falcon 9, they get the glory. But it's the smaller rockets, the prototype missiles and the sounding rockets that really acted as test beds for developing the technology that made the larger rockets and some of the larger missions possible. So we'll see this throughout the presentation of sounding rockets creating this technology that's then applied to larger rockets, and then that technology gets kicked back to create better sounding rockets. So anyways, without further ado, let's get started. What is a sounding rocket? Well, the broadest definition I can give you is a small suborbital rocket used for high altitude research, either astronomical research or meteorological research. Again, very broad definition, but the key word here is suborbital. So by definition, a sounding rocket doesn't enter orbit. It goes up, straight up and down in a parabolic trajectory. Sometimes the payload is recovered via parachute. Most of the time it's not. The rocket burns up in the atmosphere, and the data that is being collected is transmitted to the ground via telemetry. So there's two basic mission profiles that you would use a sounding rocket for. So there's a lower altitude profile, and then there's a higher altitude profile. So the profile you would use for a lower altitude mission, this is mostly for meteorology, is the zone that lies between the maximum altitude where you can send a high altitude balloon, a weather balloon, and the lowest altitude that you can successfully orbit a satellite. Any lower, the atmosphere would be too thick. The satellite would encounter a large amount of drag and it would quickly deorbit. So there's that sort of inaccessible zone there that's perfect for meteorological research for using a sounding rocket. The more high altitude profile, what you're trying to do is get above the atmosphere to carry out astronomical measurements. So for example, if you wanted to take a UV or X-ray spectrograph of the sun, you have to get above the atmosphere because the ozone layer will block a lot of UV radiation. And it's the same thing with micrometeorites or cosmic radiation or solar wind and all sorts of measurements of that nature. And for that, you need sounding rockets that can go very high indeed. Here we have on the diagram a Maxus rocket. And this is a German sounding rocket. And as you can see, its apogee is around 700 kilometers, which is above the orbit of the ISS. But certain sounding rockets like the Black Brant 12 can go even higher, up to 1,500 kilometers. So what you're probably wondering at this moment is, why not just use a satellite if you're going to go that high? Well, there's a number of reasons, the main one being cost. As you're probably aware, orbital launch is extremely expensive. It ranges between, on average, $20,000 to $30,000 per kilogram or even more. So if you get a decent-sized satellite, you can get up into the millions of dollars. And it takes a long time to develop and launch a satellite. You're looking at years of development. And this is out of reach for a lot of smaller scientific projects, such as ones run by universities. By contrast, a Black Brant will run you only $600,000 per launch. and it's a lot faster to get a sounding rocket launched than a satellite. So it's a lot more of a cost-effective option for a lot of smaller research projects. And there's a couple of other advantages as well. A satellite, by virtue of orbiting the Earth, doesn't stay in one spot for very long. So if you're just looking to study a specific part of the sky or the atmosphere, you have to wait until the satellite comes back around again. Whereas a sounding rocket, you can just launch it into that pinpoint part of the sky to do whatever research you want. And a lot of research doesn't require a lot of time in space. If you don't need a satellite that orbits every 90 minutes or so and will stay up there for years, you only need, say, 20 minutes of coast time in order to make your astronomical observations, then you can go with a sounding rocket. So again, niche applications, but very useful and very cost-effective in those applications. And before we move on, just a note on why we call them sounding rockets. So that is derived from the old term to sound, which is nautical practice where you use a sounding line, basically a lead weight on a rope, and you lower that over the side of the ship to measure the depth of the seafloor beneath you. And that turned into a generic term meaning to measure or to probe. And indeed, in French, we still say sonde to describe, say, an interplanetary probe, or we say radio sonde for a weather balloon with a little radio transmitter on it. So there's a number of different scientific payloads you can put on a sounding rocket. I've grouped them into 4 different areas of research here. So as I said before, there's high altitude meteorology. You want to track high altitude winds or temperature and pressure in the upper atmosphere and the stratosphere. And you can do this in a number of different ways. You can have instruments like anemometers or barometers or thermometers to measure the local conditions. Or if you're trying to track high altitude winds, you can use tracers. So this can either be chaff, which is of course strips of metal that reflect radar, or chemical tracers like boron or sodium. And these can be tracked from the ground either using radar or optically. Another common use of sounding rockets is for microgravity experiments. Some of the higher altitude sounding rockets, like the Black Brant 12, have up to 20 minutes of coast time at their apogee, where the payload is essentially weightless. So you can do a lot of interesting experiments. One that I've read about is where they're studying a particular type of star that produces, as part of its nuclear fusion reactions, aluminum in the form of aluminum oxide or alumina. And this sort of surrounds the star in this cloud. And in this particular experiment, to simulate that, they sent up a payload that had a little chamber full of aluminum powder. And when it became weightless, they were able to then pass different frequencies, different wavelengths of light through the cloud. And this allowed them to calibrate their spectrographs when they were actually looking at these stars. One of the main uses for sounding rockets is to study the ionosphere. This can either be for purely scientific purposes, such as studying the aurora. This is a lot of the research that occurred at Fort Churchill while that was still active, but also for practical purposes, such as studying long-range communications. And indeed, this is why the military funded a lot of sounding rocket research in the 50s and 60s, was because of, say, shortwave communications where you're bouncing radio waves off the ionosphere, and you want to know how space weather will affect that. And then there's also the issue of ionosphere heating. So when you have increased solar activity, what it tends to do is heat up the ionosphere, and the ionosphere will then expand, and it can actually expand into the path of low Earth orbit satellites and cause significant drag and cause them to lose altitude or completely deorbit sometimes. And so you want to know how to predict that and the effect of solar weather on the ionosphere. And then finally, like I said before, we have exoatmospheric astronomy, where you're trying to get above the atmosphere in order to make certain measurements where the atmosphere blocks certain types of radiation. So all sorts of scientific studies that use sounding rockets. So let's go back in time. Let's look at some history of sounding rockets. So first question is, who built the first sounding rocket? Difficult question to answer. Depends on how you frame it. Do you mean who was the first to use sounding rockets on a wide scale in order to make high altitude measurements, or who was the first to just put instruments inside a rocket? In the latter case, that would be Robert Goddard, the father of modern rocketry. And on July 17th, 1929, just outside Auburn, Massachusetts, he launched a rocket that had a little aneroid barometer and a thermometer inside of it to take some measurements at high altitude. So technically the first sounding rocket. But the widespread use of sounding rockets for high-altitude research would have to wait the development of a mass-produced and reliable rocket. And that wouldn't come until the late 1930s with the development of the Agrégat Fier, otherwise known as the V2, or the world's first operational ballistic missile. This was, of course, developed by Wernher von Braun and his team up at Peenemünde in northern Germany. During the war, approximately 3,000 of these were launched against southern England and targets in mainland Europe as well, such as Antwerp, and they killed around 9,000 people. However, the V2 has a rather dubious distinction of being the only weapon system in history to kill more people building it than in combat. And this is because, of course, they were built by slave laborers from concentration camps in conditions so terrible that 12,000 of them died building it. It was also a very complex weapon. It was not very reliable. It had a tendency to burst in midair. It didn't have a very large warhead, just 1 ton. So for all its complexity and cost, it didn't do a lot of damage. And it was just generally a very expensive weapon. In fact, the whole V2 program cost 1.5 times the Manhattan Project. And it was a big drain on resources that could have been used better elsewhere in the defense of Germany. But in the long run, it was a huge boon to scientific research and to military weapons technology because of all of the technologies that it pioneered. So, of course, after the war in Europe, there was a huge scramble by all of the Allied nations to gather up as much material on the V2 parts and blueprints and the scientists developed them as possible. And the majority of those went to the United States. In fact, as early as July 1945, some 300 rail cars worth of V2 equipment arrived in the States at White Sands Proving Ground, later White Sands Missile Range. And they were joined about 6 months later by most of the scientists who had developed the rocket, who had their paths erased via Operation Paperclip and were infiltrated into the United States through Mexico. And they immediately started a program to test and evaluate these rockets. This is called Project Hermes. And the idea was to give the US Army as much experience with the design and operation and performance, the capabilities of the V2, so that this data could inform future domestic rocket projects. So this was conducted at the White Sands Missile Range, Launch Complex 33, which is on the National Register of Historic Places now. And the first static firing of a V2 engine took place on March 15, 1946, and the first actual launch took place on April 16th. And between 1946 and 1952, they would launch 77 captured V2s cobbled together from various parts. Now, this was nominally a military operation to evaluate the V2 as a weapon, but they did allow scientists from around the country to use the V2 as a sounding rocket because they had now a vehicle that was capable of exceeding the edge of space, both defined by the military as 50 miles or via the Van Kouterman line as 100 kilometers. And so a lot of these instruments were astronomical in nature. They are typically, of what I mentioned before, instruments for measuring astronomical phenomena above the atmosphere, such as UV and X-ray spectrographs for the sun. And in carrying out this project, they had to develop a number of techniques to ensure reliable data collection. The problem with the V2 is it was, of course, designed as a ballistic missile, so it came down at an extremely high speed, twice the speed of sound, and even without a warhead, when it impacted the ground, it would just disintegrate. It would create a huge crater, and you would not acquire your instruments. And so at first, they tried to eject the instruments and recover them by parachute. This didn't quite work. It wasn't a very reliable technique. So what they ended up doing was placing explosives in the airframe. And the idea was when it came back down, before it burnt up, they would blow these explosives and it would cause structural failure and it would cause the airframe to spread out like a shuttlecock. It would fall at a slower speed and hopefully it would impact the ground with less force and they'd be able to recover their instruments. That also wasn't a very reliable method, so finally they ended up developing telemetry so that they could actually beam the data down to the ground while the rocket was in flight, and the rocket essentially became expendable. Now, other techniques that had to be developed for all of this were range safety techniques, which were in their infancy, and sometimes accidents happen. So part of Project Hermes was evaluating other types of missile technology, and the Hermes 2 was meant to test ramjet technology. So they had a little ramjet mock-up in the top of the rocket, and the rocket would boost it to the specific speed and altitude it needed for the ramjet to ignite. And on May 29, 1947, they launched this, and because the control system had actually been wired in backwards, instead of going north up the range, it went south towards Mexico and ended up crashing in Ciudad Juarez in a cemetery and blasted a crater 50 feet wide and 24 feet deep. The U.S. government had to apologize profusely to Mexico, but if there was one good thing we got out of it is this marvelous clip by Wernher von Braun, and I'll just leave that there for you for a couple of seconds. So anyway, this series of test launch actually accomplished a lot of firsts. Now, the Germans had actually been the first to exceed the von Karman line with the V-2 during their testing in 1944, but the Americans were the first to take a picture from outer space of the Earth. So this was V-2 number 13 on October 24th, 1946, and this was taken from an altitude of 105 kilometers, so just above the von Karman line. Now, some other research that was going on at the time, which may surprise you that it was going on this early, were animal tests. So on February 20th, 1947, Blossom 1 capsule in a V-2 became the first vehicle to carry live organisms beyond the edge of space. So these were fruit flies. And these were followed by a number of rhesus macaques, monkeys, all named Albert. But this was not a very successful program. As you can see, all of these monkeys died in various ways, such as suffocating because their life support systems failed, or dying on impact because their parachutes failed. It wouldn't be until a little bit later with another sounding rocket called the Aerobee that Americans were finally able to launch and recover animals safely. Yet another development of this series was the RTV-G4 bumper. So this was meant to test out techniques for staging rockets. So we had a lower stage that was composed of a V-2 and then an upper stage composed of a WAC Corporal, which is a sounding rocket we'll talk about a little bit later. And they launched 8 of these, but only 3 of them were successful. The 5th flight set an amazing altitude record of almost 400 kilometers in altitude, whereas the 7th was actually the very first rocket to be launched from Cape Canaveral, and you can see that on the right. And of course, many more would follow thereafter. Now, despite all of these advancements, the V-2 was not a very good sounding rocket for a variety of reasons. It was a first-generation design, and it was not very efficient. It was extremely heavy. It was built mostly out of steel, so it didn't have a very high thrust-to-weight ratio. It was extremely complicated. Its engine had a turbo pump and a steam generator and regenerative cooling. It was very difficult to get it to run consistently. The control system was very complex. It had a bunch of gyroscopes and accelerometers and these graphite jet vanes that stuck out into the exhaust system. And it being designed as a ballistic missile, it was designed to carry a 1-ton warhead, even though the instruments that the scientists wanted to put inside of it were never more than 500 kilograms. So what they ended up having to do was pack the nose with hundreds of kilograms of lead weight just to get the thing to fly correctly, to get the correct center of gravity. So it was really over-engineered. Surprise, surprise, it was designed in Germany, and it was just not suited to the task. So the widespread use of sounding rockets had to await something that was a little bit simpler and easier to use, and also more reliable. 66% of the rockets launched during Project Hermes failed in some way. It was not a very reliable rocket. And these would be quick to come. And actually, one of the first successful modern types of sounding rockets was developed also from a German wartime design. So in 1943, the Germans started working on something called the Typhoon, which was an unguided anti-aircraft rocket that was supposed to be fired in these big salvos to take out Allied bombers. And it had a very complicated motor inside of it. You had a cordite charge at the front that would ignite and produce pressurizing gas, and this would force the two fuels, which were furfuryl alcohol and red fuming nitric acid, into the combustion chamber where they would spontaneously ignite and propel the rocket. And they really could never get this thing to work reliably, and neither could the Americans when they captured them and started working with them. So in 1948, the Bendix Corporation decided to replace that motor completely with a solid fuel motor, and this turned it into a very reliable rocket. And at first, they tried using it as an anti-bomber weapon. They found the dispersion was just too high, so they finally replaced it with the Nike Ajax guided missile. And then the Navy ended up using the Loki as a sounding rocket. And for that purpose, they added this unpowered front stage here called the dart, so hence Loki dart. And the idea was that the first stage would burn. Once it burnt out, then the second stage would detach and it would just coast. And being a lot more streamlined and being a lot lighter, it would coast a lot farther and be able to reach high altitudes. And these were launched from a very interesting launcher. You can see it's basically an open rifled barrel. It's this launch tube with these spiral ribs that impart a spin onto the rocket. And the rocket also had canted fins to impart a spin as it flew and keep it stable. And this is a surprisingly long-lived rocket. In fact, in 1963, the Space Data Corporation developed a version of it called the Loki sonde, where they developed a proprietary instrument package to fit inside the second stage. And they continued to sell this until the 90s when they upgraded it to newer fuels and then sold it in 1990 to Orbital Sciences Corporation. And they continued to sell it until 2001 when it was finally taken off the market. So this thing survived from 1948 until 2001, and thousands of them were launched. But even before the first V2 started arriving in the United States, there was a revolution in rocket design that was already going on at Caltech, thanks to a very interesting group of gentlemen nicknamed the Suicide Squad. So these were graduate students working under Theodor von Karman, who was the Hungarian aerodynamicist after whom the von Karman line, the boundary of space, is named. And they started doing experiments with alcohol-fueled rocket motors, and the faculty got so frightened of this that they banished them to a nearby canyon so they could do their experiments and blow themselves up without harming university property. And then during the Second World War, they were contracted by the Army to create what we would today call JADO or RADO bottles, which are little strap-on rocket boosters that you put on an aircraft that's heavily laden to help it take off. And the basis for this was an innovation by one of the members, Jack Parsons, which was a modern type of solid rocket fuel. Prior to this, rocket fuel had basically been either gunpowder or cordite, so just gun propellants, and they weren't very reliable. Cordite, in particular, tended to decompose into very unstable explosives, and it didn't burn very evenly. And what Jack Parsons ended up doing was mixing roofing asphalt with ammonium perchlorate oxidizer, and it created this very stable, very even burning rocket propellant. And that's the basis for rocket propellant to this very day, although we use elastomers, like different types of synthetic rubber, instead of roofing asphalt. And so in 1941, they were able to develop the first JADO bottles. Now, after the war, they decided that they had a winning product here, and they decided to go into business, and they became Reaction Motors Incorporated, which was eventually renamed Aerojet, which was a very famous company in the history of rocket motor development and space exploration. And then the laboratory that they had formed during the war, which was called the Guggenheim Aeronautical Laboratory, eventually developed into the Jet Propulsion Laboratory, or JPL, which is still around to this day. A couple of interesting points about this group. The reason that it's called Jet Propulsion Laboratory, not Rocket Propulsion Laboratory, was because in the 30s, the term rocket had sort of a bad reputation. They were associated with Buck Rogers or Flash Gordon or, pulp sci-fi adventures. And so it was far more dignified and much more scientifically accepted to say jet rather than rocket propulsion. And that carried on to the name of the laboratory to this day. And another thing, I would highly recommend that you look up the life of Jack Parsons, one of the members of the group, because it is crazy. In addition to being a pioneering rocket scientist, he worked with Aleister Crowley, the famous British occultist, and carried forward a religion, a pagan religion called Thelema, also known as Babylon Working, where they were trying to use sex rituals to bring back the pagan goddess Babylon, bring about the end of times. I am not kidding about that. He later worked as an explosives expert for various police departments, and then he was killed in a mysterious explosion in his home lab. Another member of the group was actually Chuin Xian, who ended up going back to China and becoming the father not only of the Chinese space program, but also their nuclear program. So quite an interesting bunch of fellows. Now, other work that they did during the war, aside from JADO, was working on guided missiles. The US Army wanted to get into the guided missile game. And the first one that they built was called the Private. They named all of their designs after different ranks in the military. This was based on a Navy rocket for launching from aircraft. And this is basically just a demonstrator to show how a solid rocket missile would work. And this was followed by the Corporal. and this was the first guided missile in the US Army inventory. This was liquid fueled, so it was powered by red fuming nitric acid and aniline. And although it was a fine missile, it was very awkward to use in the field because you had to carry around refueling equipment, and the fuel was very corrosive and very toxic, and it was just not convenient to use. So it was eventually replaced with the Sergeant, which had a solid rocket motor and was a lot easier to use. Now, at the same time, they decided to try fulfilling a signal corps requirement for a sounding rocket to carry a 25-pound payload to 100,000 feet for high-altitude meteorological research. And what they ended up coming up with was the ancestor of all modern sounding rockets, the WAC Corporal. So this is very similar to the Corporal rocket in that it was liquid fueled, so again, red fuming nitric acid and aniline, but it was a very stripped down rocket. It didn't have any guidance system or attitude control. It just had these 3 fins, and those were slightly canted to impart a stabilizing spin. And so it was a lot cheaper, a lot more cost effective to use if you're just sending a rocket straight up into the atmosphere than something like a V2. And nobody actually knows where the name comes from, the WAC, the WAC. There are 2 theories. One is that it stands for without attitude control, because of course it didn't have a guidance system. The other is a little more sexist. They wanted to create something that was in between the private and the corporal, but because there is no rank in between them, they decided to go with the Women's Auxiliary Corps, the Women's Army Corps corporal. So it's because it's female, it's a little bit smaller and more diminutive. So leave it up to you to decide which is the true story. Now, at the same time, the Glenda L. Martin Company was coming up with something else, another pioneer in sounding rocket called the Viking. And this is basically a simplified, modernized V2. It ran on the same fuels, alcohol and liquid oxygen, but it was made out of aluminum rather than the steel of the V2. And so it had a higher thrust-to-weight ratio. It also, rather than those strange jet vanes, graphite vanes in the exhaust, it used gimbaled nozzles, and it was actually one of the first US rockets to actually use engine gimbling as a guidance system. And it also had attitude control at altitude in the thin upper atmosphere or in space where the fins would not be effective. And they did this in 2 ways. Roll control was achieved by jets in the fins that were fed from the steam generator for the turbopumps for the engine. They vented out these holes, and then they also had cold gas thrusters for pitch and yaw control. But despite this being an advanced piece of kit, it was also far too complicated and far too expensive still for effective high-altitude research. We wanted something a lot cheaper, a lot easier to use. So only 14 of them were built. 12 of them were launched on their own as sounding rockets, mostly by the Navy. But then 2 of them were used for another project, a little bit more famous, called Vanguard. So Vanguard was one of the U.S. contributions to the International Geophysical Year. So this was a 2-year period between 1957 and 1958, where many nations around the world would conduct research on the Earth. And so the United States wanted to launch a small satellite called Vanguard, which was actually the first satellite to use solar panels for power rather than just batteries. Now, Wernher von Braun and his team at the Redstone Arsenal in Huntsville, Alabama, had a plan already to launch a small satellite using a Redstone rocket, but that was kiboshed because of political reasons. The US government did not want a peaceful satellite to be launched using a military rocket, especially not one developed by former Nazis. So they decided to give the project to the Navy. Despite the fact that it was the Navy developing it, they developed it entirely as a peaceful rocket project. And so the first stage was developed from the Viking. The second stage from a sounding rocket we'll talk about a little bit later called the Aerobee. And then the last stage attached to the satellite was a solid-fueled rocket motor. So as you are probably aware, this didn't go so well at first. The Americans were beaten into space by Sputnik 1 and Sputnik 2. And when they finally got around to launching Vanguard TV-3 on December 6, 1957, it rather spectacularly exploded on the launch pad, leading the press to call it various derogatory things like Dudnik, Flopnik, or Kaputnik. Finally, they ended up launching von Braun's satellite with his rocket, which he had actually stashed away for just such an eventuality. So Explorer 1 was launched on January 31st, 1958. And finally, Vanguard 1 was launched on March 17th, 1958. And it is actually the oldest object currently in orbit. It stopped transmitting in 1964, but they can still track it using radar, and it's actually still used to measure the gravitational field and the shape of the Earth. So still going strong after all these years. And here you have one of those examples of sounding rocket technology being pushed forward into orbital rocket technology and being used for bigger and better things. But the first true sounding rocket, the first true reliable and successful sounding rocket was the Aerobee. So this was developed at the behest of a scientist named James Van Allen at the Applied Physics Laboratory of Johns Hopkins, and it was developed by Aerojet. And it was an evolution of the earlier WAC Corporal and of their JATO technology. So it was a two-stage rocket. The first stage was solid-fueled. It was basically an adapted JATO booster rocket. And the second stage was liquid-fueled, again, red fuming nitric acid and aniline. These were launched from 53-foot launch towers. And the reason for that was that the acceleration of the first stage was so slow that you needed to keep the rocket stable with the tower until it reached a high enough velocity for its fins to become effective in the air. And those fins had a slight cant on them, so that it was actually spin stabilized. So the first launch was on September 25th, 1947, and over the next few decades, 1,037 of these would be launched with a 97% success rate. So a very successful, very long-lived rocket, and like I said, the ancestor of all modern sounding rockets. It also, as I said before, managed to successfully launch and recover animals for the United States for the first time, and that was on September 20th, 1951, and that was a rhesus monkey named Yorick. And these could reach an altitude of around 107 kilometers. They also developed a version later called the Aerobee High that could reach 260 kilometers. And one of the interesting things that the Aerobee was used for was to validate a concept called the Sea Dragon. So this was developed by Robert Trow of Aerojet in 1962, and this was one manifestation of what's called a big dumb booster. And this is a design philosophy where rather than putting your resources into a bunch of smaller, more sophisticated guided rockets, you build something big and simple out of really cheap materials. Not the most efficient rocket, but the economics work out in the end because it's so cheap to build. And the idea with the Sea Dragon is you wouldn't need any expensive land-based launch infrastructure because you would tow it out to sea like a barge, flood the ballast tanks in the bottom, and it would launch from the ocean. It was never built, but the principle was actually proved out using an Aerobee, specially modified, that they called the Seabee. So they're able to launch it straight out of the water without any other launch infrastructure. Now, Aerobees and other sounding rockets later would be launched from a number of sites around the world. So there was, of course, White Sands Missile Range in New Mexico. There was Holloman Air Force Base, Wallops Island, which launches a lot of sounding rockets, including Black Brants today. There are sites at Vandenberg and Hawaii, Churchill, which we'll talk about in a second, and then around the world, such as in Brazil, the Bahamas, and of course Woomera in Australia, which is a big missile testing range there. Now, Churchill, the launch complex, was originally built by the US Army in 1954, and the idea was to conduct research on the ionosphere for long-range communications. So the site was chosen because of its proximity to auroral activity, as well as the presence of a Canadian Forces base nearby and the rail link, which allowed them to move material and rockets up north. So they actually shut it down originally after only 1 year of operation, after they'd launched 3,500 sounding rockets. But when the International Geophysical Year started up, they opened it up again and then closed it down again after a year once they were done with that, and then finally reopened it again in 1959. Unfortunately, in 1960, most of the complex burned down, and they had to move to Wallops Island for 2 years until they could rebuild the facility. And it remained in Army hands until 1970, when it was finally passed over to the National Research Council, and then most of the launches from then on were Canadian launches using Black Brants, and the site was finally closed down in 1985. Now, it did experience a very brief revival. There was a group in 1994 called Ecjuet Aerospace that wanted to turn this into Spaceport Canada. So they took out a 30-year lease on Churchill, and what they wanted to do was turn it into a base for launching Start-1 rockets. So these are a civilian satellite launching variant of the SS-25 Topol ICBM, Soviet design. I didn't get very far with this. They had only one launch, which was actually of a Black Brant 9 on April 28, 1998. And they went defunct soon afterwards, and the base is still abandoned to this day. So there was an attempt to revive it, but it was unsuccessful. So a little diversion here. I spoke before about James Van Allen. You probably recognize that name, and I'll tell you why you recognize that name a little bit later. So in addition to being the impetus behind the design of the Aerobee, he also made another development in sounding rocket technology. So he was working at the University of Iowa studying cosmic rays, and he couldn't get approval to launch sounding rockets from Iowa. So what he managed to do was to convince the Coast Guard to allow him to launch rockets off of one of their icebreakers that was doing a scientific cruise off Greenland. Problem was, the Aerobee was a bit too overpowered. It went too high for what he was trying to do, and any smaller rocket was just too small. So the solution he came up with to reach the altitudes that he wanted to reach, which was around 80 kilometers with an 11 kilogram payload, was to combine rockets such as the Deacon and the Loki with a balloon to create something called a Raccoon. And the idea here is that the balloon takes it up to a certain altitude, such as 70,000 feet in this case. And when you launch the rocket from that altitude, there's very little air resistance. So you increase the performance of the rocket, and you have something that's very small, compact, and easy to use. But when he tried this out, it didn't work at first. The balloon did rise to 70,000 feet, but the rocket refused to launch. So he tried it again. Same thing happened. So what he figured was that the clockwork mechanism that he was using to time the launch of the rocket was freezing up at altitude. So what he did, thinking quickly, because of course he's on an icebreaker, he goes and gets 2 cans of frozen concentrated orange juice, heats them up in boiling water to form a heat sink, and puts that in the gondola of the balloon to keep the clockwork mechanism warm. And then it works. And he manages to launch 36 of these Raccoons during that cruise. And what he discovers with the instruments on board is that at the altitudes that he's studying, there's a lot more radiation than he would have predicted, given the amount of radiation coming in from space and the sun. And this sort of confirmed his theory that the cosmic radiation was being trapped in belts by the Earth's magnetic field. And this would be further confirmed later on with the launch of Explorer 1, America's first satellite. And those radiation belts are, of course, today known as the Van Allen radiation belts. So here we have Van Allen in the middle with William Pickering and Wernher von Braun holding up a mock-up of Explorer 1. So finally, we get to the main attraction, the Black Brant, the most successful and reliable sounding rocket ever designed. So this came about due to 2 different projects going on at the same time. So in 1951, Aerojet came up with a new type of solid rocket fuel. So I'd mentioned before that Jack Parsons had come up with the idea of mixing roofing asphalt with ammonium perchlorate. In the 50s, Aerojet decided to replace the roofing asphalt with an elastomer, with a synthetic rubber that was even more stable and even more clean burning. And they entered into a partnership with Bristol Aerospace in Manitoba to further develop this technology. This ended up being kind of an ironic arrangement because the Black Brant that was eventually developed completely obliterated the market for the Aerobee. So they put Aerojet's sounding rocket business completely out of business. Now, the other development at the same time was the Canadian Armaments Research and Development Establishment, or CARDI, in Valcartier, Quebec, was trying to develop an anti-ballistic missile system. And not only the actual interceptor vehicle, but also a system to simulate the re-entry of an enemy warhead so they could develop techniques of tracking the warhead and targeting it. And for this purpose, they came up with something called the Propulsion Test Vehicle, which is the ancestor of the Black Brant. It was a very heavy vehicle, but the reason for that was that to test different configurations of fuel. And then once they figured out the correct configuration for the motor, then they would refine it into something lighter. And they contracted Bristol to help out with this, and they actually ended up transferring that project completely over to them in 1961. And so the first Black Brant that they developed was the Black Brant 1. It could launch 68 kilograms to 150 kilometers in altitude. Not great, but not bad for the time. And then they continued to develop this. The Black Brant 2 was just a 3-fin version of the Black Brant 1. Black Brant 3 had 4 fins and could go to much higher altitudes. But this took a long time for it to develop because it had stability issues both in the engine and in the airframe. So that didn't really enter adoption until 1964, after which they flew around 66 of them before moving on to other designs. So here's the Black Brant family. The current Black Brant model is the Black Brant 5, and then everything beyond that is a combination of the Black Brant 5 and other various boosters that are strapped on. Now you're probably wondering what happened to the Black Brant 4. Up in the upper left here, that's a Black Brant 4, and that is a Black Brant 5 first stage with a Black Brant 3 second stage. So you can see the vast difference in diameter between those two rockets. And then the Black Brant 8, you add a Nike booster. Black Brant 10, you add the Nika, which is sort of an interstage that fits onto the Black Brant 5 itself. You can add a Taurus or a Talos, different types of rocket boosters to get to higher and higher altitudes, with the highest altitude version being the Black Brant 12. Now, another thing you'll notice, where are Black Brant 6 and 7? Those were tiny little Black Brants that were developed for the Army for high altitude atmospheric research. So they wouldn't actually go into space, they would just go up into the stratosphere. But these didn't last very long. They had a lot of development issues, had a lot of stability issues, and the Army decided they were too expensive and scrapped them. And here you can see sort of, again, this feedback loop between sounding rockets, operational rockets, and missiles, and then back to sounding rockets. So for example, the Talos booster is off of a Navy shipborne guided missile. The Nike boosters, of course, off one of the first guided anti-aircraft missiles. And when those became surplus, then they were rolled back into sounding rockets and used as surplus boosters. So the cycle comes full circle. Now, just to explain the advantage of the Black Brant, it all has to do with the fuel. And modern composite rocket fuel has two basic ingredients. One is an elastomer. Today it's known as hydroxyl terminated polybutadiene. It has the consistency of pencil erasers. And an oxidizer, which in this case is ammonium perchlorate. Sometimes they will add another fuel to add energy. In this case, this would be very fine aluminum powder. And you can instantly tell when a solid rocket motor is burning aluminum because it produces a lot of white smoke. And that's aluminum oxide in the smoke. So the space shuttle strap-on boosters used that type of fuel. So that is cast into a metal casing. And some rockets, some smaller ones, are end burning, where it's just a solid block of fuel and it burns from one end to the other. But typically they'll have a port or a channel down the middle of the grain, and it'll burn from the inside out. And the reason for that star shape in the port is for burning consistency, because the pressure inside the rocket and the burning rate is dependent on the surface area of the fuel that's actually burning. If you have a perfectly circular port and it increases in diameter, that's going to increase the surface area, and the burning rate and the pressure is going to start increasing throughout the burn. With that star shape, as you can see in the diagram in the lower right here, as it burns, the surface area actually stays pretty constant, which means that you have a flat burning curve, except for at the very end when you have the little slivers of fuel left in the corners, and that drops off very rapidly. So it's very even burning, and it's much easier to predict the performance of the rocket and how high it will go. So a major competitor for the Black Brant at the time was a subject I've covered before in an extensive lecture, which was Project HARP, which was, of course, the brainchild of Gerald Bull. And what he was doing was using a large modified naval gun out in Barbados to fire projectiles called martlets, which were encased in a sabot and had either chaff dispensers in them or instruments that could take measurements at high altitudes. And the reason for this being a huge competitor is because compared to a Black Brant, which costs you $600,000 per launch, firing of the HARP gun cost you only $500 per launch. But unfortunately, it was done in by Gerald Bull's hatred of politicians. He didn't like politicians. He made a lot of enemies in the Canadian government. And they were all too happy to oblige by cutting his funding and causing the whole project to be canceled by 1967. And there's reason to believe that they were also protecting their own investment, because they had invested millions upon millions of dollars into developing the Black Brant. And this was one way of cutting out the competition and ensuring a market for that Canadian product. Now, a little bit of personal history. Back in 2010, while I was still studying engineering, I actually worked for a summer at the Magellan Rockwood plant, which has been in operation since 1963. And this is where the Black Brants are made, along with a number of other rocket motors like the CRV-7 rocket pod weapon. It was an interesting job. It wasn't as exciting as you might think. My job was to update manuals. So I had to go out onto the production line and take pictures of people working to make sure that what they were doing was in line with the production procedures. But interesting place because, again, it has not changed since the 1960s. All of the equipment is pretty much original. And it's interestingly laid out. You can see from the satellite image, all of the various buildings are all widely separated. And you really can't see them from the road because they're surrounded by an earthen berm. And this is because they're dealing with highly explosive material, especially the ammonium perchlorate and also the mixed fuel. Once it lights, it doesn't go out until it's all burned up or all exploded. So those berms are to prevent explosions from causing a chain reaction to all the other buildings. And most of the buildings also have big blowout panels to vent the explosion in case there's ever an accident. So again, interesting job, not as exciting, but an interesting place to work. Now, we finally get to the Black Brant's other major claim to fame, which is nearly causing World War III. So the Norwegian rocket incident occurred on January 25th, 1995. So there was an early warning radar station at Olenogorsk in northern Russia, and they detected a contact rising from the Arctic Ocean and heading towards Moscow, and it fit almost exactly the profile of an American Trident missile launched from a submarine. And as it reached its apogee, they could see a little piece of it breaking off, and they interpreted that to be the MIRV, the Multiple Independent Reentry Vehicles, being launched from the missile. At first, they were a bit skeptical that this was an actual attack because they thought, well, why wouldn't they launch multiple missiles all at once? But then somebody suggested, well, what if they're doing an EMP attack? What if they're launching their warhead into the upper atmosphere to generate an EMP pulse that will blind the Russian defenses? So they phoned it in. The warning reached the Kremlin, and President Boris Yeltsin was handed the Shaget, which, as you can see here, it was the Russian nuclear briefcase. In the States, it's called the football. And he opened this up, armed the transmitter, which was to send an order for a counterattack. And he was just about to launch Russia's missiles when the radar station finally detected that this object was going north, not towards the Arctic, and was not going towards Moscow. And so they dropped the alert, and everybody stood down. It turned out, of course, it was a Black Brant 12 launched from the Andøya rocket range in Norway. They had tried to alert everybody in the area, but the Russian government apparently didn't get the memo. And that is one of the closest shaves we've ever had in terms of nuclear warfare. It's the only time that any country's nuclear briefcase has actually been opened, armed, and ready to go. And this actually occurred several years after the end of the Cold War. So a dubious claim to fame. So since the 60s, around 1,000 Black Brants have been launched, and they have a 98% success rate. They're one of the most reliable and successful sounding rockets ever designed. Like I said, Fort Churchill is defunct, so most of them are launched on behalf of NASA, the Canadian Space Agency, sometimes the European Space Agency, from either Wallops Island in Virginia or the Andøya rocket range in Norway. And that's it. I'm going to, if everybody wants to unmute, I'd be more than happy to answer your questions.
Yes, can I ask a question?
Yeah.
Gilles, did you say the Black Brant rocket that we have at the Aviation Museum? I don't know whether you remember it. What model is? Do you know what model it is?
I think that's a 4 because it's about the only one that had that stepped configuration where it was a Black Brant 5 mated with a Black Brant 3. So it's a 4.
Okay. Now, did you say that Magellan are still making them, but not? Are they still made in Winnipeg?
Yes. Well, not Winnipeg. The Rockwood plant is just north of the Stony Mountain Penitentiary. But yes, they're still made there to this day. Not very many. I don't have an exact figure for how many they make per year, but if you do the math and say, okay, 1,000 of them have been launched since 1965, it works out to less than 20 per year. And it
Okay.
makes sense because they're all made by hand. There is no automation whatsoever at that plant. All the insulation on the inside of the rocket casing is laid up by hand by a single person. All the propellant is mixed by hand and poured and cast and inspected. They're all immaculately handcrafted.
Yeah.
And the process has not changed in 60 years.
Okay. Now, I know that you've already told us this, but tell me again, why is this called a sounding rocket?
Oh, because to sound, to take a sounding used to be to drop a sounding line over the side of a ship. So you have a lead weight on a rope, and then to sound the waters became the term for to probe something, to take a measurement.
Okay.
So it's a very archaic term that's still used to this day.
Okay. One more question.
Sure.
I'm sure you're aware of what Elon Musk is doing in South Texas right now. He was the first one to actually achieve bringing back booster rockets and also major big rockets back to Earth safely to one location. I mean, why wasn't that perfected until now? I mean, you'd think that would be an obvious procedure that to be done with a rocket.
Because it takes very precise control systems, and we really haven't had the processing ability, the cheap processing ability to do that until very recently.
So how do you think he uses like a homing device, or do you think he uses just GPS to land in a certain area?
I believe there is a homing device on like a homing signal on the pad, especially when he's landing on drone ships out at sea. So there's a very sophisticated tracking system. So it's a combination of the processing power and the control systems that you need to achieve that, because you have no margin for error. And also, there hasn't really been a need until now. Like once you breach that hurdle and you're able to do it consistently, then yes, you save money. But you have to breach that hurdle, and it's very expensive in testing. So nobody wanted to do that before because it was just cheaper to throw out boosters to make them expendable.
But yet he's gone to NASA and he said, I can build the same thing that you're building for 1/10 the price that you're making it for.
Well, in that case, Elon Musk is full of bluster. So it may or may not be the case that he can.
Gilles, for a number of years, Magellan was one of the displayers at the Rotary Career Symposium. And they feature the Black Brant rocket. It's a part of that display. In fact, they had a smaller, I guess it would have been a scale model of the Black Brant, about 5 feet tall. And at one point during the display, somebody walked in, picked that model up, put it under their coat, and walked out with it. People helping them all the way, opening doors and things. And they never, ever got it back.
Okay.
Yeah, I've heard that story.
Yeah.
Well,
I've heard it from 2 or 3 people, so I'm thinking that this is probably true.
Gilles?
Yeah.
Gilles.
Al Parkin here. I was interested in the point you made about the V2 costing more Manhattan project, which is pretty amazing given that all the labor was free, forced labor. But I have a question related to that. What project on the Allied side cost more than that project?
Sorry, can you state that again? Like how much, like which in cost in terms of money or in terms of lives?
Yeah, no money. What on the Allied side cost more than the Manhattan project?
I'm actually not sure.
Yeah, it's the B-29 project.
I'm not surprised.
Yeah.
Gilles.
Yes.
I was amazed to find.
Many years ago, when I was going to SAIT here in Calgary in the 1960s, Dr. Fia came and gave a talk on the Black Brant. And I, before the talk, I thought I better bone up on this. So I went into the library and I read everything that I could, which wasn't much. And so after his presentation, I asked a question about the Black Brant, and he said, where did you get that information? I said, Jane's all the world airplanes. Well, if you'd actually gone to a reliable source, which broke up everybody.
Yeah, so he was the chief developer of the Black Brant. He was actually asked by the president of Bristol, Murray Old, in 1958 to be to head up their rocket division. So he was the chief engineer in charge of the early part of that project.
He was quite the person. Yeah.
So I've heard.
Jules, I'm sorry to ask you another question, but
Don't be sorry. That's what I'm here for.
So I think a lot of rockets use Raptor engines, but when they leave Earth, they're using the oxygen from Earth. But if a rocket was to be ignited in pure vacuum of space, does it have do you have to bring your own oxygen, sort of thing?
Oh yes, of course. That's what rocket engines are for. So the idea of a hybrid air-breathing engine is that, you do in a normal rocket, you're carrying your own oxidizer along with you for the entire ascent up into space. Yeah. If you don't have to do that, if you can use a ramjet or a scramjet engine and use atmospheric oxygen for most of your ascent, then your rocket can be a lot lighter. But once you do get into space, then yes, you have no source of oxygen. You need to carry your own oxidizer with you. Okay. And all current rockets, like from the 40s onwards, have just carried their oxidizer, whether it be liquid oxygen or something else, on board and just burn that all the way up through the atmosphere and up into space and while they're in space.
Okay.
Gilles?
Yes.
Question. And this is naive. I don't know anything about this, but it's always intrigued me. Whenever I've watched a rocket blast off, I've always had that sort of the sense of doom and wonderment at how the hell all that fire, all that fuel, all that incredible explosion doesn't just disintegrate every single time one of those things gets launched. What is it about the technology that prevents that?
There's all sorts of things. Like their rocket engines can have all sorts of failures, and one of the main innovations, and this is something that the Germans really perfected during the Second World War, is regenerative cooling, because you have extremely high pressure and extremely high temperature at the throat of the nozzle. And if you make that out of pretty much any material, it's going to melt. Like, it's extremely hot and it's going to melt. So you need to cool the engine in order to stop it from melting, especially if you want to use lightweight materials like aluminum. You want to make the rocket as light as possible. Right. So what they do is they pump the fuel into channels in the engine bell, and it absorbs the heat from the combustion chamber, and it also pre-pressurizes and pre-energizes the fuel. And then once the fuel has absorbed all that heat, it's then injected into the combustion chamber, and the heat ends up leaving with the exhaust. So
really, so the fire we see that's extending beneath the rocket is distant enough from any additional fuel or part of the rocket that would incinerate.
Yes, exactly. You're getting rid of most of the heat. And remember, heat has to transfer in one of three ways: conduction, convection, or radiation. And so it's not going to transfer by convection, because the rocket is moving past its exhaust. You can set it up so that it doesn't transfer by conduction, like by adding insulators or arranging how everything is connected up. And if you don't have a engine bell material that's very radiative, it's not going to transfer by radiation either. So it's all about, where does the heat go, where does the energy go, and how can you get it away as quickly as possible so that it doesn't overheat. Yeah.
What happened in the Challenger accident?
So that was the boosters, so the solid rocket boosters, and those were not monolithic, like they were not built in one section. They were built in multiple sections spliced together with O-rings. And because the Challenger launched on such a cold day, those rubber O-rings became very stiff.
Brutal.
And so the hot gas from the rocket motor was able to leak out through the joint. And then that leaked out into a little jet of flame into the liquid hydrogen and oxygen tank, causing that to rupture. And then the whole thing ruptured and the spacecraft disintegrated.
My gosh. It just, to me, every time I watch video or film of these things, I marvel at the miracle that the damn things just don't explode completely.
And it's lots of trial and error. Like if you actually look at the records for like even the Germans during World War II, most of their rockets blew up. Like for months and months and months and months, they would blow up. And then once in a while they would get a success and it's okay, what did we do there? And it's just incremental development where you have to get every little thing working correctly. So like I don't have the statistic on me. I wrote a video about this a while ago, the Atlas missile, when they were testing that, like it was for a good 2 years that they didn't have many successful launches, but the engineers like to say, oh, well, every part of this has failed at least once, but never more than 3 times.
So I won't dwell on this too long, but to go back to the point the link you made to the, I guess it was the V2, which is closest to a rocket, correct?
Well, it is a rocket. Like the V2, like the difference between missile and rocket is what are you using it for? Like a missile is a rocket that you put a warhead on.
But I guess the final sort of corollary question was, the Germans mastered that separation you were talking about to keep the damn thing from exploding and still propelling the distance required to get to the target.
Oh, they perfected more than that. So they perfected the turbo pump, which is needed to pump the fuel at a high enough rate into the combustion chamber to get the thrust you need. Like you can do it with pressure, like by just using pressurized helium or nitrogen to force the fuel out, but that only works up to a point. And if you want to get more thrust, then you need a turbo pump, which is kind of like the turbo on your car. So you have a turbine in the middle that's run by high pressure steam, and they would generate that by mixing hydrogen peroxide with sodium permanganate. It reacts very violently to produce high pressure steam and oxygen. You run that through the central turbine, and that turbine is connected to 2 other turbo pumps, and those pump the fuel through. Because these are rotating at such a high speed, they need to be very precisely made and balanced, and the bearings need to work even when you're pumping cryogenic liquid oxygen through them. So that was one of their big developments. The gyroscopic stabilization of the missile, how do you keep it on course? How do you make sure that the engine cuts off at the right altitude and speed and attitude so that it will actually land on target? The aerodynamics, what shape do you make the rocket so that it can go through the sound barrier, that it can re-enter the Earth's atmosphere without burning up? They had to solve pretty much every problem that you can think of. And
how many did they successfully launch?
I don't know about test launches, but I do know that they launched, like I said, around 3,000 during the war, but they had a very high failure rate. So around 60% or more of them failed in some way. They either blew up on launch or shortly after launch, or they broke up on re-entry. And they would launch thousands of them before that, both at Peenemünde and in Blizna in Poland. Actually, one of the problems that they had was that they would airburst. They would blow apart when they came back through the atmosphere. And the reason for that, I won't go into too much detail. It's the shape of the rocket was wrong for re-entry. It caused a lot of heat from re-entry to be deposited on the fuel tanks, causing them to swell and burst. And they couldn't figure out why this was happening. So what they ended up doing was giving it what they called tin trousers, which was just a big steel tube over the fuel tanks that would keep them rigid long enough for the heat to dissipate and keep the rocket all together until it could reach the ground. So it was a Band-Aid solution, but it worked.
Yeah. Thank you for those very interesting responses. Fascinating.
Oh, no problem.
Question?
Yes.
Ted, if you want to read an interesting little story about the Challenger disaster, I mean, Richmond, Gilles will know of, did an interesting little to explain it. There's a couple of videos on YouTube. Google Richard Feynman, Feynman, Challenger experiment. You'll be fascinated by him.
Thanks,
Yeah,
Al.
so just to summarize that, it was the commission that was organized to investigate the Challenger disaster. So they brought in Richard Feynman, very famous theoretical physicist, and NASA was obfuscating. All of their scientists and engineers were obfuscating, trying to say it's very complicated. We don't know what happened, and we couldn't have predicted it. And he comes up with a glass of ice water and a sample of the material that the O-ring was made out of, and like a C-clamp, and he clamps the little piece of O-ring material in the clamp, dunks it in ice water for a couple of minutes, pulls it out, and shows that it does not spring back into shape, that it becomes very rigid. And
Wow.
that completely changed the course of that investigation, because now it was out in the open, like nobody could contest that. It was an amazing piece of showmanship. And the commission just they could not deny that.
We have the Challenger Commission.
More than Thiokol happy with the result.
Yeah, no, well, there was an engineer at Thiokol who knew about this. They knew about this for years beforehand. And interestingly enough, if you look at footage of earlier launches, there had been burn-throughs before. You could see them on the camera tracking the shuttle. They knew about this for ages. But because what had happened was that when the O-ring material started to burn, it formed this sort of slag material that plugged the gap. So it would automatically correct itself. It would plug its own leak. But during the Challenger disaster, there was a bit of wind shear, and that wind shear dislodged the plug, and it allowed the flame to exit again. So it had plugged itself, and then it was dislodged, and then the flame came out again, and that's what destroyed Challenger. So it's just that little bit of wind shear that was the difference between them making it into orbit and not.
But Gilles, wasn't it also an engineering decision to put the space shuttle right next to two great big bombs, the booster and the fuel tank, instead of on the top of a rocket like the dinosaur was originally intended?
Yeah. So I hate the space shuttle. It was a mess of compromises from beginning to end. All sorts of things. Like I was commenting today because it's the anniversary, they're posting pictures of the crew, and they didn't give them spacesuits, like launcher entry suits, until after Challenger. They went up in like nylon flight suits and crash helmets with no oxygen.
Yeah, it mattered anyway if it came apart.
No.
Yeah, the point is that when that happened, it wouldn't have mattered what you were wearing, because you would have been thrown out into the atmosphere and you would have died in the fall. And believe me, at 10 Gs, you're not going to be able to go, oh, gee, I have to pull the ring for the parachute.
Although there have been successful ejections from the SR-71 at Mach 3.
Yes, there's no way that you could put ejection seats into the shuttle.
They did on the first two test flights.
Yeah.
And how else would you get out?
Yeah. Well, actually,
they
how
they
rope,
did, didn't they?
Yeah,
I think they had a rope so you could go down by rope.
Yeah, the current system is a little bit goofy. You open up the exit hatch on the side and you pull a handle, and this inflatable boom inflates, so it goes over the wing, and then you hook up like a zip line to it. And the idea is when you jump, the boom carries you over the wing so you don't hit the leading edge, and then you parachute out. But you have to be in level flight for it to work. So there's only a very narrow range of conditions during an actual flight where you can actually escape the space shuttle.
Yeah.
And if you've ever been in one, the space shuttle is gigantically oversized. I mean, it's the size of a DC-9, where all you really needed was a smaller vehicle that would do the same job.
Well, the reason for that was that the Department of Defense said that they needed it to be able to carry large surveillance satellites. So the shuttle was trying to be all things to all people, and that was the whole point. It was supposed to be a space truck. It was supposed to be able to carry anything, anywhere.
Like the capsules in the space station.
Yeah, but the thing is, like that's proven technology. Like that's the reason they went back to capsules, is because, especially the reentry, the heat shield, the space shuttle, of course, with Columbia, where they had endless problems with the heat shield on it. And so they decided to go back to capsules with an ablative heat shield, which is proven technology. It's simple and it works.
Yeah.
Question.
Jill,
Yeah.
Jill, in your presentation, you mentioned the International Physical Year, Geophysical Year.
Yeah.
What was that all about?
It was international cooperation to study the Earth, to better understand the Earth. So you had things like the Mohole, which was the attempt to drill into the Earth's through the Earth's crust into the mantle by drilling through the Earth's crust at its thinnest, which was like at the bottom of the ocean. So the Americans, they sent out this drill ship and they tried to drill through the bottom of the ocean. It didn't work because it's like, I heard it described as trying to drill a hole in the pavement from the top of the Empire State Building using a long strand of spaghetti. It doesn't work. So all sorts of different countries had different projects where they were doing geophysical experiments. So it's supposed to be this big like scientific spirit of international cooperation. And they wanted to launch Vanguard as part of that. The Russians ended up launching Sputnik 1 and 2 as part of that.
Stood on the end, and then the drill.
And that was in the 1950s, was it?
Yeah, that was 57 to 58.
We're going to start wrapping up now, Gilles. If there's any
Sure.
other last questions.